In this particular problem, I want to take a look at a situation where we'll continue to build upon our model and see how the number of solutions can vary depending on the number of constraints that we have. Each constraint, as we've seen, leads to a single equation. And so the question is, what happens if we have too few of them or too many of them? Now, we've seen the effects, but we'll make that a little bit more apparent in an application here. So let's take a look. An industrial manufacturer receives shipments of parts. In each shipment, there are 642 bolts, 170 cotter pins, and 694 lock washers. Ideally, each shipment will be used entirely to build the products the manufacturer sells. So here are the three products. A small motor requires 3 bolts, 1 cotter pin, and 5 washers. A mid-sized motor requires 8 bolts, 2 cotter pins, and 10 washers. And the largest motor requires 16 bolts, 4 cotter pins, and 7 washers. So the question is, what are our unknowns in this situation? Well, it kind of depends on the question. Assuming the manufacturer only produces small and mid-sized motors, how many of each? There's our question. So that helps us define our variables. How many of each would it be able to produce? Well, since we're only focusing on small and mid-size, I'll create 2 variables, and we can call them x and y, or x1 and x2. So I think I'm going to go with x1 and x2 for this problem. And x1 will be the number of small motors to produce. And x2 will be the same thing, but it'll be the number of mid-sized motors to produce. Okay, so the question then remains, what are our equations going to, what are our constraints going to be? Well, if we think about increasing the number of small motors, well, that's going to use up more parts. It's going to use up more bolts, cotter pins, and washers. Our limitations correspond to the number of bolts, cotter pins, and lock washers that we have available. So our constraints are right here. That is constraining, literally constraining, it's restricting how many of each of these we're able to sell. Now, if we think about the number of bolts, so a small motor, mid-sized motor, they use 3 bolts and 8 bolts. So let's just focus on the bolts equation first, because we're going to have an equation that says, hey, we've got to use up all of our bolts, but we can't use more than that. So each small motor requires 3 bolts. So the units of this would be 3 bolts per small motor. Well, it depends on how many small motors we make. And the number that we're making, we defined it to be x1. So if I, for example, made 10 small motors, then that would require 30 bolts. Let's look at now where the bolts are going to be used up for x2. Well, that's the number of mid-sized, and each one of those uses up 8 bolts. So that's going to be 8 times the number of mid-sized motors. That'll tell us the total number of bolts that we'll have to allocate to building the mid-size. And then if we add these quantities together, this will give us the total number of bolts for the small motors, plus the total number of bolts for all of the mid-sized motors. And we know that we want that to equate to 642, since our objective is to use up all of the parts. Now we'll have another equation, and that equation will be for cotter pins. For cotter pins, same kind of idea. 1 for each of motor 1, or for the small motor, multiplied by the number of motors. So again, if we made 10 of them, it would require 10 cotter pins. And for the second one, it's going to require 2 cotter pins per mid-sized motor times the number of mid-sized motors. So if we made 10 there, it would require 20 cotter pins. And we want to use up all of them, which is 170. The next equation that we're going to have is going to be for washers, and that's our last one. And for washers, I'll just go ahead and skip to the chase here, and we'll have 5x1 plus 10x2 equals 694. Now, if we take a look at the system, we only have 2 quantities that we can control, x1 and x2. Yet what we're trying to do is we're trying to satisfy 3 different constraints. So the more constraints you place on a small number of variables, the less likely it is to have a solution. And if we furthermore think about these 2 equations as being lines in 2 dimensions, where we have an x1 and x2 axis, then the likelihood that all three of these lines intersects in the same spot is not highly probable, just by chance. So already we're probably going to imagine this will most likely not have a solution. But we would build our matrix 3, 8, 642, 1, 2, 170, 5, 10, 6, 94. We would produce the reduced row echelon form. And already I can tell you we are going to end up with one equation that's going to have 0, 0, 1. The other two equations are going to result in 1, 0, 0, 0, 1, 0. Whenever you see this form, don't jump to any conclusions about the solution yet, because remember, just because this has ones along a diagonal does not necessarily mean anything. In fact, this suggests, if we were to read this off, this says x1 equals 0, x2 equals 0, and the false statement 0 equals 1. This, of course, as a collection of equations is false, and therefore this results in no solution. And our system is what we call overdetermined. Overdetermined means that, as I mentioned earlier, we have more equations than we do variables. We have more constraints than those variables are able to control. So imagine that you wanted to make the perfect sound out of a stereo and you had two equalizers that you could play with, that you could play around with the bass and the mid, but even when you play around with the bass and the mid, it's not going to really allow you to get the highs or the treble-y sounds in your configuration. So you'll be very limited in terms of what you can do with it. And same thing here. Fewer variables than we have equations will often lead to what we call overdetermined systems. Now, the concept of no solution, we call that kind of system an inconsistent system. And it happens because the system is overdetermined. Given all three sizes, let's look at a variation of this. How many of each would it be able to produce? Okay, so now if we're doing the third motor as well, keep in mind that the equations, and I'm not going to rewrite all of the equations because for x1 will still be the number of small motors to produce, and those require 3, 1, and 5 bolts, cotter pins, and washers. Now this is corresponding to motor 2, 8, 2, and 10. But now I'm going to have not a fourth equation because I don't have another part constraint. I have another unknown. So we're going to define this third variable, x3, to be the number of large motors to produce. Okay, and so what will that do? Well, the number of bolts will be 3 for each of the small motor, 8 for each of the mid-sized motor, and now we will have 16 for each of the large motor. So we would basically have 3x1 plus 8x2 plus 16x3. And again, we only have 642 bolts in total. Now for the second equation, 1 cotter pin per small, 2 cotter pins per mid-size, and 4 cotter pins per large, and we have a total of 170 available. This will be 5, 10, and then 7 for the number of washers, and we only have 694 of them available. Now notice that we have the same number of equations as we do variables. This does not mean that we'll have exactly one solution, but there's a better chance that will take place. So if we went ahead and reduced this, what we end up getting is 1, 0, 0, 38, 0, 1, 0, 42, and 0, 0, 1, 12. So what does this mean? Well, this means x1 equals 38 small motors, x2 equals 42 mid-sized motors, and then we should have x3 equals 12 large motors. And because we do have a solution, we can say that this is a consistent system. Consistent means that a solution, at least one solution exists. If there's no solution, that's when it's inconsistent. As far as it's determined, I guess, we usually use the phrases overdetermined or underdetermined. And let's take a look at another example where we actually will see an instance of an underdetermined but consistent system. So let's imagine a fourth extra large motor is added requiring 24 bolts, 2 cotter pins, and 10 washers. How many of each can it make? Is there a minimum/maximum for the number of each? Again, just like in problem 2 where we added a column for a new motor, now we're going to need a new column for this fourth motor, and this is going to be the number of extra large motors to produce. And our matrix, okay, it's going to be the same 3 columns to begin with because that's corresponding to x1, x2, and x3, the number of small, mid-sized, and large motors. But now the number of bolts will also be determined by how many are used up here. And since that's going to be 24, imagine we'd have 3x1 plus 8x2 plus 16x3 plus 24x4. That'll give us the total number of bolts we use among the 4 motors. We want that to be 642 in total. As you might guess, this is going to be 2 and 10, and our constants have not changed, so those are going to be the same. But now notice that we have 3 equations, we have 4 variables. This typically will be an underdetermined system, meaning that the information, the constraints, are inadequate to fully specify the exact values of the variables. That's going to often lead to a free variable. And indeed, when we produce the reduced form of this system, we notice that we have a non-zero pivot in each of our rows. So x1, x2, and x3 are fully determined, but notice there is no row in which x4 has a leading 1, right? So that's actually impossible, and this is the way you can imagine why it's going to be infinitely many solutions is there's no way each of our variables could have a non-zero pivot. Meaning that if there are only 3 possible rows for pivots and there are 4 columns of variables, you're going to end up with at least 1 free variable, assuming there is a solution, because it could also be a case where there's no solution, but it's going to be no solution or infinitely many solutions. And so therefore, x4 is free to vary. So we would say, let x4 equal some constant, some real number. And now we could write out our solution vector. Know that x4 is just a constant. Now x3, well, x3 is actually fully specified. x3 has to be 12. So you have to make 12 of the large motors in this case. x2 is going to be 42 minus 9 times x4, which is the free variable, so 42 minus 9c. And x1 will be 38 plus 16c. So there's our solution for all of these different values of c that we could pick. And now, there are mathematically infinitely many solutions, but we have to think about this contextually, and perhaps there'll be a minimum and maximum. Now, as far as the parameter that we have, c, that's what we really want to focus on here. So what happens if, well, c we know is going to be the value of x4, so we know that already there's no way that c could be negative. So the next question is, could c be 0? If I plug in 0 for all of the c's, I would get 38, 42, 12, 0, and there is nothing wrong with that. Sure, that leads to not producing any extra large motors, but we didn't say we had to. So the minimum C would be 0. And then there's also going to be a maximum value for C. And the maximum value for C would be determined by what we have going on here. Because notice that as I increase C, x2 is going to go down. So I can ask myself, for what value of C will this be equal to 0? And that will tell me the maximum value of C. So if I solve this and I get 9C equals 42, C equals 42 over 9. That means that you cannot make, for this to be greater than or equal to 0, that means C would have to be less than or equal to 42 over 9. Now 42 over 9 is just a little over 4. 4 2/3, I believe. Yeah, 4 2/3. So actually, practically speaking, you can't have 4 point something. You can't produce 4 point something extra large motors. So we'll say that C has to be less than or equal to 4. As long as C is less, and you can double check here, 42 minus 9 times 4, that's 30. 42 minus 36 is 6. 6 is bigger than 0, but as soon as you make C equal to 5, well, then you're starting to get negative numbers. So the maximum C that we could have is 4. Again, because of we're talking about quantity of motors, can't have fractional motors. So as far as what this leads to, when C is 0, let's just take a look at x1 through x4. Okay, because these are going to be the extremes. So x3, no matter what, is 12. x1, if C is 0, then that would lead to 38 of the small motors. And when C is at its maximum, that would be 38 plus 16 times 4, which is 64 plus 38, 94, 102 would be the max there. Now, for x2, it's going to flip because when C is at its smallest, then x2 will be at its largest of 42 units. And when C is at its biggest, 42 minus 36 would give us 6. And then x4, well, x4 will be as small as 0, or it'll be as big as 4. So you can see what the mins and maxes are. Here we just have to flip these, right? And 6 would be the minimum of the mid-sized motors, and then 42 would be the largest of the mid-sized motors. And this is what we call a consistent system because it has solutions, but it is underdetermined. If I can spell it, determined, meaning that there aren't enough constraints to fully determine the system, that we could have another constraint. Unfortunately, we only have 3 of them because we have constraints on 3 parts, but when we have fewer equations than variables, we're typically going to get an underdetermined but consistent system.